So I will talk about k-nearest neighbor classification. But before I do, I should say, what is classification in general? So for classification, you are given a training set where the observations are numbered with this index I, and xi are the so-called features. So these are values that characterize your object of interest, and then there are labels. And for classification, the features, they could be continuous, or they could be discrete, or they could be categorical. Whereas the labels, and this is the distinctive property of classification, must be categorical. So there is a hierarchy of different types of numbers. If we just think of numbers, single numbers, at one extreme we have continuous numbers. Then we have ordinal numbers such as 1, 2, 3, 4, where 2 is more than 1. And then we have categorical, which does not imply any kind of ordering or preference. So, for example, apples and pears would be categories, and pears are not by themselves more or less than apples. This is what's given and wanted in classification. Is a good prediction or mechanism for making good predictions for new observations. By new, I mean observations for which we have only the features and we want to predict the correct label, and what is good or not is measured by a loss function. Now, if we can go to this screen, please. I have drawn an example of two features, x1 and x2, and I have encoded the labels with colors, and this would be an example of, a pretty much unsolvable problem. Perhaps there is a tendency of having more red points in the bottom left corner than in the top right, but looking at this, you will not be able to come up with a valid predictor. So, in other words, the best classification algorithm in the world cannot do anything if your classes overlap too severely in feature space. I've now added a third informative feature to this data set, and lo and behold, the data does become separable. It's perhaps not totally or not linearly separable, but at least the overlap has been much reduced. Now, finding good features or creating good features is not something the machine can do for you. This is at the discretion of the expert. So, let's say you are in industrial quality control and you want to decide if the part is good or not. If your camera just looks the wrong way, the algorithm cannot do anything. So, first of all, you want to have the camera look at the piece that you want to judge. Secondly, it may so happen that under this illumination, given this camera and giving this kind of part that you want to study, it simply does not show up if the part is intact or defect. So what could you do? You could add a second camera, or you could operate under different lighting conditions. So either have different lights positioned at different places, or you could have lights of different color. So you need more, in any case, you need somehow more information or more features that will help discriminate the classes of interest from each other. Coming back to this competition that I mentioned. You remember this Kaggle or this Heritage Health Prize competition. Just to take that as an example, I've downloaded some of their data, and I need to somehow bring it to a screen which you can see. So these are, for instance, the features that they provide. In this competition, the task is to predict who is going to spend time in hospital next year. And the people are characterized by a number, by a set of numbers. So a member ID, which is hopefully not predictive, then different numbers, and then you see what kind of treatment they underwent, how long they stayed at an institution that was treating them, with what condition they entered that place. You also find how old they are, how long it took them to pay their bill, and so on. And probably some of these features are more predictive than others. So let's say this pay delay, it could have different explanations. If we argue about it, we could say either this is because people were lazy, and probably laziness is not such a good predictor for, to say if you're going to end up in hospital next year. It could say that these people had a harder time coming up with the money, so they were poorer. That could be predictive. It could be something to do with age, that perhaps you have more forgetful and less forgetful elder people, but age we have as a separate feature, and so on. Yeah? Now the beauty of this machine learning is that we don't need to somehow come up with a rule by ourselves, but we just take that historical data. So we take these, I think it's 2 million entries in this, or 2 million observations, along with the outcome. So historically, this is the treatment that they underwent, and then I have the information in the following year, did they have to go to hospital or not? And we can take this bunch of data, the training set, and extract rules that will hopefully allow to make good predictions. So if it so happens that the best algorithms in the world fail to make good predictions based on these numbers, then you will simply need to add more information. For example, where does somebody live, and things that are not currently encoded. So I've basically been repeating for 3 or 4 minutes that the crap in, crap out principle. So if the features that you put in are not predictive, then the best algorithms are not going to help you. And the extraction of the features or the providing of the features, that's not something the machine can do automatically for you. It's up to you, to the human operator, designer of a device, to come up with these features. Okay, so I've been preaching enough about that, I think. So let's talk about our first classifier, the one nearest neighbor classifier. By the way, NN is also often used to abbreviate neural networks, so you have to go by context to see what people were trying to tell you. And, well, this is a simple algorithm which is best explained in terms of pictures. Here's what it does. We have some features. We have some points. We partition feature space according to which point lies closest, and this is a tessellation of feature space. So definition of tessellation means a set of non-overlapping areas which taken together make up your entire space. To the physicists here, this is known as the Brillouin zones in solid-state physics. In computational geometry, it's called the Voronoi diagram. Now, if we have to make a prediction, let's say at this point, what the one nearest neighbor classifier suggests is to simply look up which point lies closest and to copy the label from that point in making the prediction. So if I want to make a prediction here, I will predict the red class. If I want to make a prediction here, I will predict the blue class, and so on. So it's an extremely simple recipe, which I think many people will agree is, sort of, it intuitively makes sense. So in words, for each new datum for which we want to make a prediction, we predict the class membership of the closest training sample. By the way, this Voronoi diagram is never constructed explicitly, but it's still useful to understand what the algorithm does. So, a couple of properties. The algorithm is extremely simple. Probably there's nothing simpler than that. And it's actually not so bad. If you have enough observations. However, this is especially true in low dimensions. So if you have, 2 or 3 features. Here by performant, I don't mean efficient in the sense of making fast predictions. I mean performant in the sense of the prediction quality is not so bad. It's also not state of the art, so it's not what people would really use. However, if you just want to know, roughly, do these features make sense, or you don't have any software around, and you're sitting on an island with your computer, no internet connection, and you need to program something quickly, then why not do that? There are why not do that? One thing is that it's very, very slow. So it's you can think of it as a lazy strategy. You have 0 effort at training time, and lower than that you cannot get. But then you have all the effort at prediction time. Most algorithms or most state-of-the-art algorithms operate differently, so they take quite a long time to train, but are then very, very fast in making predictions. Another thing to realize is that the empirical error, that's defined as the number of errors, the number of wrong predictions you make in your training set, this empirical error, well, as long as points from different classes do not lie in exactly the same position, what will it be, this empirical error? You can talk to your neighbor, and we have an opinion there. Yeah, exactly, the empirical error is always 0. Well, always, you know, let me put a star there. So as long as points from different classes do not perfectly coincide. So the empirical error is always 0. So in other words, looking at the empirical error on your training set does not tell you anything about if your features are sensible or how you will do when you are going to make true predictions. And this really highlights the importance, which is particularly pronounced for one nearest neighbor, but is generally important for all classifiers, the importance of distinguishing between training and test set. We need to distinguish between the empirical error, the one on the training set, and the predictive error or generalization error. That's the error on a separate test set. And we will talk about that in more detail during the semester. Then another thing to note is that the decision boundary will be very rough. Rough is not a technical term. Can we have the screen once more, please? So if we had a well, what do I mean by decision boundary first? Decision boundary means the set of points where you cannot decide if you would predict this class or that. So the decision boundary in this case, it's a subset of this Voronoi tessellation, and I'm tracing it out with my hand here. So it's always where a red and a blue area meet. This is the decision boundary. And now a single datum or a single observation has the power to change this decision boundary. For example, let's say if I had a single example from the blue class right here in the middle, this would create a small island, so my decision boundary would become even more complicated. Would you want your decision boundary to look like that for making predictions? Probably not. You wouldn't want that island in there. The island, you know, is not wrong in the sense that the two classes may have overlap, and however, it's unlikely that if you now get a new data set, you would have a query sample at exactly the same location. I'm not making myself very clear, so I'm showing a different picture here. I have here generated I've drawn two different training sets from the same underlying distribution. So in principle, I should get the same decision boundary here and there. However, you know, these outliers or these some of these points all of the points are in a different position in these two plots, and so the decision boundary, what we would really like to see is that here we have the blue class and outside we have the red class, but what we get now is this very complicated decision boundary with these tiny islands that we would like to get rid of, that we should get rid of. So that's what I mean by a rough decision boundary. And what these two plots here already illustrate is that we have a high variance, and that is now a technical term in one nearest neighbor classification. Variance means how different do your models look, or how different are the classifiers that you get out, depending on if you look at one training set or on another training set, at another training set, even if these two training sets come from the same underlying distribution. So high variance is bad. On the other hand, it also has low bias. another technical term. And later on in the semester, now I've just said in words what it is. Later on in the semester, I will give really the more technical definitions of variance and bias. Low bias is good. Bias means how much if I now average across very many training sets, how much does your average classifier differ from the ideal classifier? So overall, you could say that this method is a little bit unstable, or it's very sensitive to individual data points. Now, how can we help that? I hope you have a suggestion, or you might have guessed from the slide that I showed. Exactly, take more neighbors into account. Very good, and you've invented a new method. This is the previous one was one nearest neighbor, and now we have k nearest neighbors. So typically k is an odd number, and you then make a democratic decision. So let's say we look at the 5 nearest neighbors, and then we decide democratically, depending on a majority vote, if we want to predict this class or that. Now in this particular example here, if we take 5 nearest neighbors, we still have some islands, and if we now take a very large number of neighbors, at some point these islands disappear, which is good. Can you think of anything bad happening if you make k too large? Yeah. Yeah. The boundary can become too smooth. So what if so let's say I need color now. Let's say that the true distribution of the classes unknown to the algorithm looks like that. So this is the distribution in feature space of the red class, and here I have the distribution in feature space, whatever, of the blue class, and I've not indicated the density per se. In this pretty picture that I've drawn, the two classes are even separable. Yeah, they do not overlap. But if now, for instance, I want to make a prediction at this point here, can you show the screen? Or how do we do that? Or no, I can, sorry, Bernhard, I'll do it here, otherwise we get a tunnel. So if I now have to make a prediction at this point here, I should really predict the blue class. But if I now ask for a very large number of neighbors, I have to take into account points from a larger radius, and I will on average find more red than blue, so I would make the wrong prediction. I would have smoothed over the fine details in the ideal decision boundary. In these more technical terms, it means that k nearest neighbors has a lower variance. So the decision boundaries that I will get will look more similar as I go from one training set to the next. But we pay for this by an increased bias. Let me call this increased bias an underfit or an underfitting to the data. Okay, so perhaps k equals 1 is not so good. K equals, infinity doesn't make sense, but k equals 1000 may also not make so much sense. So how do we choose the ideal k? What would you suggest? talk to your neighbor, please, and get back to me, or you have one? Yeah, and can you specify test? Yeah, exactly. So sorry for insisting. I wanted to hear the error on the test set. Yeah, so you want the separate test set where you know the labels, but you don't show them to the algorithm, and you simply repeat these experiments until you found the number that gives you the lowest error on the test set. That's, you know, a viable strategy if you have enough data to afford entertaining a separate test set. If you do not have enough data, then you can, for example, use cross-validation, which we'll talk about in a few weeks. Now, well, look, we've already done our first classifier. There are a couple of variants to this. None of these variants are very widely used, but well, they certainly do speed up things and may perform well in some settings. For example, there are many variants, but I'm only mentioning one here, which is called condensing. It works as follows. You first select a training sample randomly. And put it in a reduced set, or put it in an active set. And you then loop over the samples. And you do the following. If this current sample is classified correctly, by a nearest neighbor classifier that uses only the samples in the active set for training, so if it is anyway classified correctly, then you can discard the sample. Else you add it to the active set. So the rationale behind this is that in this example here, the decision boundary would, for instance, not change if I eliminate this point, or if I eliminated that or that or that point. In fact, for the one nearest neighbor classifier, it is only these defining samples, or it is only, you could call them support vectors. It is only these points that define the decision boundary, and the others are not needed. Even so, this algorithm is not as ideal as it perhaps looks at first sight. Can you think of a problem? Can we go back to the sheet, please, Bernhard? Yeah. Yeah, so we could get a bias through this procedure. Actually, it was only proposed, I think, for one nearest neighbor, probably for the very reason that you mentioned. So it's a bias sampling strategy, yes, or it can be. What else? So will we always get the same classifier out if we do this? Is this an exact or an approximate method, essentially, is my question. Talk to your neighbor if you like. Okay, so who has suggestions? So, yeah, go ahead. Excuse me? Yeah.
Let's say you, in your active set, a point that's close to the decision border, and then you categorize another point of that set, which is not active, as part of this feature, or its label, and you say, okay, I don't need this point, which is directly at the decision border. So you change the decision border.
Yeah, exactly. So the decision border can be changed, and it depends on which sample we start from. So we had this, we selected the first sample randomly, and then we had a loop over the samples, which also is a random order. So overall, what we have is an order dependence. So order dependence means your outcome depends on the sequence in which you presented the observations. This is bad, but this whole thing can lead to much faster predictions. So it can give us a speed up, which is good, of course. And what it does overall is that it tries to retain only the most relevant, or tries to retain only relevant points for classification. And this is why I would like to call these relevant points support vectors. And that's a bit of a, well, some people would call this an abuse of language or terminology, because support vectors are usually only associated with a technique called support vector machine, which we'll also study. But I think the basic principle here is the same. All right, so let's discuss this efficiency issue and how it can perhaps be increased. Yeah. Yeah. Okay. Sorry, by sample here, I meant one member of the training set, so one observation, so 1 point, 1 dot in this. Yeah, I'm using a few words here interchangeably. So sample for me in this context would be the same as observation, would be the same as datum, would be the same as example. Okay. Sample has two different meanings. On the one hand, people use it like I just did when I want to refer to a single training object, single example. And on the other hand, one can say, we draw a sample from a distribution, and then it means you know the whole collection, the whole set of objects. And because so many people have contributed to this field, it's perhaps not so surprising that some of the terminology clashes, and people sometimes have different words for the same thing, or even worse, mean different things when they say a thing. We just have to live with that. Okay, so how about the speed? I said this was a slow method. Can you give me the computational complexity of making a single prediction? So let's say I have a training set of size n. If I take a naive algorithm, how long will it take to make a single prediction? Let's say with 1 nearest neighbors. Again, please talk to your neighbor for a minute. And okay, so efficiency of a single prediction, what do you think? Or, sorry, complexity of a single prediction? Any suggestion? Do you have one? Yeah, so naively, the complexity would be order of the size of the training set, exactly. Now, if we let's stick with that naive approach for a moment, and let's see how we can do this practically. I have written some MATLAB code here. So I create a distance matrix with it's interesting. It's not what I see here. Okay, wrong screen. Sorry. So I've created a set of points here, 1,000 points, which are three-dimensional, and I've just created random points, and I want to compute the matrix of square distances. I use the square distances to save computing the square root. So if I want to compare distances, I can do that up to any monotonic transform. So I omit taking the square root, and actually here I've done this redundantly. So I've done this redundantly because I've computed the full distance matrix, even though of each point to every other, even though it is symmetric here. Anyway, if I do that, let's look at this on MATLAB. So if I do this, well, I've run this just before I came to the classroom. If I do this, it takes 3 seconds. And if I use this other bit of code, which is also MATLAB, so it takes 0.03 seconds. So it's 100 times faster. So what's happening here? What's different? And the thing is that this naive way of just doing it with a double loop in interpreted languages is very slow. You know, it gets a little less slow if I let it run from not from 1 to n, but from I to n, and if I or I plus 1 to n, and if I afterwards mirror my matrix to profit from the symmetry. But such loops tend to be slow in interpreted languages, and however, these languages, they call underlying linear algebra routines, and they are very fast. And I want to, tell you roughly how to exploit that. So let's say if I have two sets of points, I have a set of points which I call A, p dimensions and n points, and I have a set of points called B, p points and m dimensions. And I now want to compute a distance matrix, or a matrix of squared Euclidean distances, and that will have, let's say, n rows and m columns. Sorry, this D should be in the middle. Okay, I want to have the squared Euclidean distance between each of the points in A and every of the points in B. And to do that, I can look at a single matrix element. These vectors here are row vectors. And I can just write that out as okay, and I'm talking here about the ijth element. So let's say this was I, and let's say this was j. And you see that I can now assemble this full matrix D at the same time in terms of matrix operations by replicating the vector holding all these informations for the different i's, by replicating the vector that has all those informations, and by creating this matrix here. And this is what has happened in a tiny piece of MATLAB code that well, I need to find for you. So you don't need to, or don't try to copy this down right now. You will get this again for the exercises. But repmat is a MATLAB command which simply means replicate this vector. I could have also written this in terms of linear algebra as an out product between a vector and between another vector of just ones. So I replicate, let's say this is a row vector, and I replicate it across the rows. This is a column vector which I replicate across the columns, and this entire thing is a matrix. It's an outer product between a column and a row vector. No, it's between. This is a matrix product, which then has these dimensions m by n, and altogether, this gives me this matrix of squared distances. So I've done too much work here because I've not considered the symmetry, or no, here I no longer have it, not necessarily, because I have two different sets, so there need not be any symmetry. So here I've used or I've expressed this simple calculation of computing all the square distances in terms of linear algebra, and that makes it 100 times faster. So this is, it's mathematically it's the same. It's just for interpreted languages, that's a more efficient way of writing down the computation. So essentially, this was just a MATLAB trick. I opened the parentheses and I closed the parentheses. Now, independent of the programming languages, there are other ways to speed up the computation. And one is by not looking at all points and finding the closest ones, but to partition space iteratively. So let me call this here speedups. And one possible speedup is by using a so-called KD tree. What a KD tree does is that it recursively partitions space, or in our case, feature space, by axis orthogonal cuts. And I have not specified how these cuts are reached. One possibility is to look at the spread in each dimension and then make a cut across that dimension which had the largest spread. Or you can take the median point, or different recipes. So this is my feature space, and this split here is orthogonal to one of the axes. And now I do this recursively until I have sufficient fine granularity, or until I have a maximum number of points in a given leaf. And if I could draw more prettily, then all of these things here would be truly orthogonal. I apologize for that. Okay, those are supposed to be all be orthogonal lines. So if I now take, if I now want to make a query, let's say at this point, I first descend this partitioning tree to find out in which leaf the point resides. So this generates a binary tree. So the first split here was this node, and let's say this was the second split, and let's say those were the third and fourth splits. And for completeness, let's continue this. Sorry, some overlap here. And this tree happens to be perfectly balanced, but that need not be so. So let's say I could introduce another split here, just to make the point that this would be split number 7. Just to make the point that the tree can be deeper in some places. The tree can be deeper in some places than in others. Sorry, this would be number 8, not 7. Okay, so if I now want to find the closest neighbor for this point here, what I can do is I can ask, does it lie to the right or to the left of my first split? And the answer is, it was lying to the right. And then I can ask, did it lie above or below the second split? And the answer was, it was lying above the second split. Oh, sorry. 3 happens to be this child, so I have to go in this direction here. And then I'm asking, does it lie to the left or to the right? of this region, and let's say that left means it ended up here. So each of these leaves of the tree corresponds to one of these regions in feature space. So now I found that my point is here, and now I can search, for instance, amongst all points that lie in the same leaf, which is the closest neighbor. And let's say the closest neighbor is this one here. Now I can check if there are potentially any points on the other side of that split that lie any closer than the current one. So the current closest distance is this one, but the distance to the split number 3 was very large. So I can exclude that there are any points on this side which could be even closer. So it means I can simply disregard this entire branch of the tree here. But now I have to go to the next parent and ask, could it be that some of the children of node number 2 are closer? So I'm asking if this sphere here, if it intersects with the split number 2. And unfortunately it does. So I need to descend also towards the children of 2. This is a process called backtracking. Okay, and if we use this backtracking, we can eventually really find the closest point, and we can rule out parts of the tree that we know are definitely too far. Unfortunately, in this example here, or in this judiciously chosen point, I have to visit quite much of the tree. Yeah, so I have to visit the other side of split number 2. I even have to visit the other side of split number 1, because at least in the way I drew this distorted hypersphere here, it could potentially be that there's a closer neighbor on the other side of split number 1. So the good news is that this can be fast, in particular in low dimensions. So this is the difference between, expected complexity and worst case complexity. It can be fast in low dimensions. The bad news is it's almost certainly not faster in high dimensions. So why have I stolen your time in telling you about it? Because it illustrates the fundamental problem of finding, or it explains why it is a problem to find close neighbors quickly in high dimensions. And some people go so far as to say that finding close neighbors quickly in high dimensions is currently the biggest problem that we have in pattern recognition. I wouldn't subscribe to that view, but just to tell you that this is an important problem. Why is it almost certainly not faster than linear search in high dimensions? The reason is that these funny spaces, these rectangular spaces, are not a good approximation to a sphere, and they become even worse approximations in higher dimensions. So in high dimensions, there's a very, very great probability of finding some point that is on the other side of a split, but is even closer to your current point than all the neighbors in the same leaf. Okay, so with these moderately good news, let's have a break here. And after the break, I will tell you about yet another speed-up technique, and we'll sum up k-nearest neighbors. And we'll then, in the second part of today, come to more principled way of doing classification. those are spill trees. And another reason I'm talking about that is everybody who has followed algorithms and data structures lecture knows the KD tree, but the spill tree is a little less widely known. So the spill tree, the KD tree provided an exact tessellation. Yeah, so what we get from the KD tree is an exact tessellation of space, and as long as we use backtracking, the algorithm is exact. That changes with spill trees. With spill trees, you use a redundant representation. And renounce, on the other hand, on the backtracking. They use instead a greedy strategy. And this is no longer exact, but only approximate the solution that we find. So how does it work? I again have a set of points. I'm omitting the labels. We just want to find the closest neighbors here. Yeah, go ahead. Oh, renounce at backtracking. So we no longer do backtracking. So we again try and find a split. Let's say this is the split. But now I do not uniquely, before I just split my space into two halves, I now separate it into two overlapping regions. I will on the one hand split it into a blue region. And on the other hand, into a red region. And these regions are allowed to overlap. So if I again draw the corresponding diagram, I had my black node, which corresponded to the split. And now I have two children, a blue child and a red child, and let me symbolize this overlapping by say that these childs are not totally separate. These children are not totally separate. Now, this also happens recursively, and trying to draw it becomes a mess. So I'm not sure I should do that. So I could now, take the blue region and partition it again, but the two children of the blue region would again have some overlap, and so on. However, this time I do not do backtracking. So let's say that my query point lies here. It lies on the right of the first split. It lies to the right-hand side of the black split. So I decide to look in this blue region here, and I am looking for the nearest neighbor in the blue region. And at this point, I no longer backtrack. So let me change the problem artificially by introducing an extra point here. So let's say I want to make a query here in the traditional and the closest neighbor that I would have found using the KD tree would have been this one here. But the closest neighbor that I now find using the spill tree is actually that one, which lies on the other side of the original split that I performed. However, it's still in the same region. You see, I'm in the blue region, and the blue region now extends up to here. So this is an example where I have successfully found my true closest neighbor without using any backtracking. But of course, you can construct examples easily where this goes wrong, and that's why it is only an approximation. And what people now really use in practice are so-called hybrid spill trees. Where you alternate proper splits and redundant or soft splits. So and they also do other things. They also use random projections I'm not going to talk about today. I'm also not going to talk about it today, but I want to mention it once. An alternative to all these business of spill trees is locality-sensitive hashing. You don't really need to copy it. I just want you to have heard the term already. Locality-sensitive hashing, abbreviated as LSH. That's also a popular technique that helps in finding close neighbors. All right. Do you have questions? Go ahead. Yeah, good question. Where do we get all these splits from? People propose different criteria here. One possible criterion is, I'm going back to the picture with the KD tree. One possible criterion is to really alternate between the axes. I could say I first want to split along the horizontal axis, and I then I sort the points along this axis, which is an n log n operation, and I then pick the median, so the point that lies in the middle, and make my first split here. I next, and I happen to have drawn the tree in that way, I next decide to make vertical splits on both sides, and I again partition on the median. And in this picture, this is also roughly the strategy that I have followed. But it is by no means the only one. You could think of different things. You could compute, for example, the spread in each child. So originally, the root of the tree, it comprises all samples. So you could compute the spread along each dimension and then say you want to split where the spread is maximal. And you could do that at the center of mass, for instance. But this will be sensitive to outliers, or you have different ways of measuring spread and so on. So there is no universally best recipe of constructing these trees. So people experiment with different things and report that some heuristic works better than others, but in the end, those are just heuristics. More questions? All right. So I want to summarize the k-nearest neighbor. Not so much the algorithm in itself, but we have discussed actually we've come across a number of interesting points. So my summary regarding its performance was, let's say it's a decent classifier, but slow. And interesting points that we've come across, and that we come across in most methods, is so far I always implicitly assumed that we're using the Euclidean distance. But that need not be ideal. In particular, in image processing, people use not the Euclidean distance in feature space, but other distances, in particular the tangent distance. So there's the choice of similarity or dissimilarity measure. It also has to do with the scaling of feature space. So, if you measure different properties, if I use Euclidean distance, let's say I have a couple of points and I want to do a nearest neighbor classification, and I could have measured the length of something in meters and the weight of something in units of kilogram, or I could have measured this length in millimeters, which would have spread my data 1,000-fold in the x direction. If I use the Euclidean distance to find the nearest neighbor, this makes for a huge difference. Yeah. So on the one hand, I have my circle of points which have the same distance from this point, and if I now switch from meters to millimeters, if I plot in the original coordinate system, I now get a neighborhood which is squeezed by 1,000-fold. So the units of these features really matter when we use Euclidean distance. So, or more generally speaking, the user needs to decide on what is a good similarity measure in this particular feature space, and that is a way of injecting prior knowledge. So you can look at it both ways. You can say this is bad because it requires arbitrary user decisions, or you can say it is good because it allows you to bring in what you know already about the problem. Then something we saw was, how do we set k? So we have this choice of the parameter, which some people call user parameter, or it can be called the design parameter, or it can be called the hyperparameter. In our case, this number of nearest neighbors, k, that we're looking at. We saw this issue of training versus test set performance. So how important it is, and it cannot be stressed too many times, because so many people, and intelligent people, they fit a method on their data and then they report the quality of their fit, and it's totally meaningless, as the one nearest neighbor classifier brings out especially nicely. So you really need a separate test set or some other means of estimating generalization performance. We've looked at different algorithms that may help improve the efficiency, and we've also talked about algorithms that are approximate, and that raises the question, how good an approximation is this really? And overall, this is a method which is intuitive, but as I have presented it, it bears no relation to any deep concepts in the way I presented it. So that's why later today we still want to talk about statistical decision theory, which tells you what classifier is better than another one. Any final questions for Kenyo's neighbor?